Okay, for number 2, we have a car, and its mass is 10 to the third kg, and there's a force acting on it of 5 times 10 to the third newtons. No frictional forces. And I want to know first, how long does it take to get to 30 meters per second? I'm assuming I start from rest, and I want to know how long that takes. Okay, so how do I do this problem? I've given no distances, so I can't use work. Energy is not going to work. But I can see straightforward that force equals mass times acceleration, and I have force and mass, so I can get the acceleration. And then I know the change in velocity, so I should be able to get time. So acceleration is equal to force over mass, which is equal to 5 times 10 to the third newtons over 10 to the third kilograms. These cancel, and this is kilogram meters per second squared, and I have 5 meters per second squared, a reasonable acceleration for a car half of gravity. Now I also know that acceleration is equal to the change in velocity over change in time, and so the change in velocity, which is equal to v final minus v naught, the change in velocity must be acceleration times change in time. Oh, right, so I got this. Change in time is equal to v final minus v naught divided by acceleration. Right, but maybe I didn't need the formulas. I could have just looked at this and said, look, I'm changing my velocity 30 meters per second, and it changes 5 meters per second every second. And so you can see it's going to be 6 seconds when you carry that out. Then I want to find the average power for that whole 6 seconds and the instantaneous power. And this is at 30 meters per second. Okay, so what is power? Power is equal to the change in energy over change in time. And so how is the energy changing? It's gaining kinetic energy. And so that would be energy final minus energy naught divided by that change in time, that's 6 seconds. So that's going to be 1/2 mv final squared minus E naught, which is 0, it's not moving, divided by that 6 seconds. So putting in the numbers, 1/2 times 10 to the third kilograms times 30 meters per second, don't forget to square that, divided by 6 seconds. And maybe what I want to do is cancel this with one of the 30s, so this will wind up being a 30 times a 30. This cancels, giving me a 5 here. And so I have 5 times 30 is 150, times 1/2 is 75 times 10 to the third is equal to 75 times 10 to the third watts. Is it watts? Kilogram meters squared per second squared, because I square that. That's a joule per second is a watt. So that's 75 kilowatts. Or, oh wow, 100 horsepower. So that's the average power put out over this whole 6 seconds, the total change in energy over the total change in time. Now for the instantaneous power, that would be the power output at t equals 6 seconds when velocity is equal to 30 meters per second. Right? And what we could do is we could just say this is a change in energy over the change in time at that 6 seconds. So that would be equal to the energy at 6.001 seconds minus the energy at 5.99 seconds divided by 0.002 seconds. One more 9. Or I could just recognize, we remember the formula is energy, change in energy is a work done over change in time. We remember that work is a dot product of force and displacement, and power is that work divided by time, we can take this and see that's velocity. So power is the dot product of force times velocity at that moment. That's going to be 5 times 10 to the third newtons times 30 meters per second. And what do you end up with? 5 times 30 is 150. That's 150 times 10 to the third, so 150 kilo. And a newton meter is a joule, that's a joule per second, and that's a watt, which is 150 kilowatts. All right, so what we see is the instantaneous power at 30 meters per second is twice the average power. And that should make sense because when I start out at zero velocity, even though I have a force, the rate of energy change, the power is zero. So I start out with zero power output, finish with 150 kilowatt output, and the average power over that whole period of time is 75 kilowatts. So there I am, minding my own business, moving along at 30 meters per second. A reasonable highway speed, that's about 66 miles an hour, right? And I hit this person who just doesn't know what's going on. And they're sitting there at V equals 0 and 2,000 kilograms. This isn't pretty. What happens? I know this is conservation of momentum because there's no outside forces in this collision, and momentum initial must equal momentum final. It's true, I conserve energy here too, but energy changes form, and I don't know, in this collision, very likely energy is changed to heat. So what we have at the end is this whole box moving along, 3 times 10 to the third kilograms is moving in this direction, with some P final is equal to mass final times velocity final. And I want to know what that velocity is. So let's find out. We know that P naught is equal to P final. What's P naught? Oh, it's just this guy. This one has no momentum. So this is mass times velocity is 10 to the third kilograms. I forgot my units. Times 30 meters per second, which is 3 times 10 to the fourth kilogram meters per second. And so I know that has to be the momentum of this guy, and so I can just write it out. 3 times 10 to the fourth kilogram meters per second is equal to mass final times velocity final. Okay, and I can recognize that these are vectors, and that I can define this as the positive x direction, and I'll make this a positive x vector. And now I just have to divide through by this mass, and I have V final is equal to 3 times 10 to the fourth kilogram meters per second in the x direction, divided by 3 times 10 to the third kilograms. I love it. Everything cancels except this 110 here, because this is a 3 and that's a 4, and I wind up with 10 meters per second in the x direction. We stop for a moment and say, does that make sense? That this should go along at 1/3 the velocity of the initial car. This is a big fat car, a little skinny car. Goes like this. I can imagine that happening. For D, what we want to know, does the energy after the collision, energy final, equal the energy before the collision, the initial energy? And we remember we start with all the energy, all the momentum in this 10 kilogram mass. Then there's this collision, bam. And we have this conglomeration of two cars moving along at 10 meters per second. And so we can just calculate this kinetic energy. Energy naught is equal to 1/2 mv squared, 10 to the third kilograms, times 30 meters per second squared. That's 900 meters squared per second squared. 1/2 of that is 450, so that's 450 times 10 to the third kilogram meters squared per second squared. That's a joule, right? And this I can say 1, 2, this is 5, so 4.5 times 10 to the fifth joules, 450 kilojoules. So that's my energy before. Go through and calculate the energy after if you want, but we can recognize that kinetic energy is equal to 1/2 mv squared, or that's the same as p squared, the momentum, over 2m. And we can compare before, when we have this guy moving along, to after, when the mass is 3 times as great, but the velocity is 1/3 as great. And so you can say, look, I know the momenta of these are the same because I conserve momentum. I know momentum is conserved. And so the mass goes up by a factor of 3. The kinetic energy must go down by a factor of 3. And I can say kinetic energy is proportional to 1 over the mass in this situation, in the collision. So the kinetic energy final is going to be 1/3 of this because the mass of the moving body went up by a factor of 3, and that's 1.5 times 10 to the 5th joules. Where did the energy go? There was a whole bunch of work done on the metal, ultimately turns to heat. I mean, there's sound as well, but that's very small. And that's going to be heat given off is equal to the difference of kinetic energy, which is 3 times 10 to the 5th joules. Is that a lot of energy? I don't know. Let's see. I know that 4.2 joules is about a calorie, which is enough energy to heat 1 gram of water up 1 degree Celsius. So let's say this is about 4.2, and divide by 4.2 joules per Kelvin, and so it's about, a little bit less, but about 10 to the 5th calories. Okay? So that would be enough energy to raise 10,000 grams of water 10 degrees Celsius, or 10 liters of water 10 degrees Celsius, and that's about 2.5 gallons of water 10 degrees Celsius. Is that a lot of energy? You decide. In any case, that's not really what I asked you in that question. Is I asked you how the work in from the engine compared to the work out on the road. And so we look at the energy flow. We started from the work of the engine. That turned to kinetic energy. And I said there's no frictional losses, right? So the work of the engine turned completely to kinetic energy, and then there was a collision. And so we went from the kinetic energy of 1 car to the kinetic energy of 2 cars. And that turned to work on the road. What I'm asking you to accept is there's no frictional losses here, that all of the energy was lost right here. So when I ask you how this work compares to this, it's going to be the same as that kinetic energy comparing to that kinetic energy. Now something that's interesting is that the engine put a force in this direction and moved us over a displacement in the positive direction. So that was positive work done on the car. Now when it was slowing down after the collision and the brakes locked up, it continued to move in this direction until it stopped. But the force of the brakes was slowing it down. And so it was doing negative work on the car. And hence, the change of energy was negative. But where did that energy go? The energy could have gone into friction heating up the road. But we could have made use of that energy. How could you make use of the energy of slowing something down? If the car was here, we could have slowed it down, for instance, with a paddle wheel. Right? And that would have been connected to a generator. And as it slowed down, that energy could have gone into electricity. So rather than being lost in heat on the road, you could have lost that kinetic energy, you could have converted that kinetic energy to some other usable form.